Hi there. As you can see, I'm out today due to a foot injury. Hopefully I'll be back soon. Thought I would give you guys some notes on free body diagrams. Free body diagrams. So free body diagrams are used to analyze forces, okay? And the only thing we put on them is forces. All the forces that are acting on the object, and only the forces that are acting on the object. We want to be able to show the magnitude and the direction of each force. And we'll do that with arrows, of course, because it's a vector, and a dot. You'll see some free body diagrams with boxes, but dot's the real one. Also known as FBDs. Okay? All right, so imagine a book sitting on a table, right? We got a picture here, got a book sitting on the table, and we want to draw a free body diagram of the book on the table. So let's list the forces that are acting on the book. We've got force due to gravity, and we've got, and that goes down, right? And we've got the normal force of the table pushing upward. Okay, so you draw it like this. The dot is the object, and then I would draw from the dot, so start on the dot for every force. I would go down FG and up FN. And I would draw these two arrows equal and opposite because the book is not accelerating vertically, so it shouldn't have a net force vertically. This way it has balanced forces and a zero net force for zero acceleration. For example, if the mass was, I don't know, like 1 kilogram for the book, someone could ask, is it accelerating? You know, is it accelerating? And we could prove it mathematically by adding up the forces. So we would want to sum up the forces in each direction. In this case, we only have the y direction, so we could straight up write some of the forces in the x direction, 0. Some of the forces in the y direction will be Fn plus Fg. Well, what's Fg? We can just use Newton's second law to determine the force due to gravity, or the weight, and like so. That would be 1 kilogram multiplied by negative 10 meter per second squared. And we could see that the weight of this book is 10 newtons. Go negative. And then we could label those on our free body diagram. Negative 10 newtons. And I would automatically know that the normal force is also 10 newtons because it's not accelerating vertically. I could prove that mathematically here by plugging them in. 10 newton plus negative 10 newton. 0 newtons. And if I further want to show that the acceleration was 0, I could use Newton's second law. F equals ma. Negative 10. Oops, I should solve symbolically first, of course. A is equal to F over m. Let's put our nets there. You'll also see it like sum of the forces over m. Right? Still directional. Can only do one at a time. We would have 0 newton divided by the mass. 1 kilogram equals 0. Equals 0. So we could show that this book is not accelerating vertically. And that is the free body diagram. Here's another one. Wait, I'll do another video so it's easier to put on YouTube. See ya.